Okay, so today we have Ignacio Carreño Bolla, who will tell us about the 5D tangram, brainwebs, 7 branes, and primitive T-codes. Take it away.
So, first of all, thank you, Julius, for giving me today the chance to talk here at the Quiver Meeting. So, today's talk will be based on this recent paper that we wrote with my PhD supervisor, Diego Rodríguez Gómez, and also Sebastián Franco. So, before we start, let me give you an overview of what's the structure of this talk. Well, the main topic will be 5D SCFTs, which can be studied in two main ways. For example, we can construct them via so-called brainwebs. These are a Type IIB configuration of 5 branes that meet at a junction. Or alternatively, we can do geometric engineering on a singular Calabi-Yau threefold. So we take M theory and we put it in this background. Now, these 5D SCFTs have an extended Coulomb branch, which can be seen in either picture as either taking the brainweb junction and opening up into irreducible webs, or alternatively resolving the singular geometry of the Calabi-Yau. Now, a natural question to ask is whether there exists a fundamental piece of this extended Coulomb branch, which we claim that it does, and it is given by the so-called T-codes, which were originally introduced in the mathematical literature. Now, these T-codes correspond in the brainweb point of view as irreducible triple junctions of 5 branes, or equivalently as smoothable singularities in the Calabi-Yau threefold. So they can be, this singularity can be removed in some sense. Now, using these T-cone pieces, we can construct extended Coulomb branch of GTPs, which are theories that are closely related to toric geometries. By tessellating the integer polygons that defines these GTPs with some puzzle pieces made from T-codes, kind of like puzzle in the tangram puzzle. Finally, we will talk about how to think about Hanany-Witten transitions in these two images. Well, a Hanany-Witten move in brainweb corresponds to taking an external sembrane and crossing it through the web. We claim that the corresponding geometric engineering avatar of these are one-parameter deformations of the theory, where the exceptional fiber corresponds to the theory before crossing and the general to after crossing. And we will support this hypothesis with an explicit example realized through the 5D BPS quivers of some GTP theories that reduce to toric cases. Now, more concretely, this talk will be split into 3 parts. First, some background on brainweb geometric engineering and GTPs under SUSY conditions. Then we will introduce T-cones and the role they play in the extended Coulomb branch. And finally, we will talk more in detail about this so-called algebraic deformation that realizes Hanany-Witten moves in the BPS quiver. So let's start first with the introduction. Now, the existence of 5D SCFTs is a non-trivial fact coming from string theory, as shown by Seiberg back in '96. Now, these UV SCFTs often accept relevant deformations to infrared effective gauge theories. This is because the Young-Mills coupling in 5D is irrelevant, so these theories are non-renormalizable. As I've just said, there are 2 main ways to construct them. First, we can take M theory and take it into this background where X6 is a singular non-compact Calabi-Yau threefold. So the non-compact condition decouples gravity, and the data of the theory that lives in this transverse Minkowski's case is encoded in the singularity. Alternatively, we can use brainwebs, which are a system of type of PQ 5 branes, that is bound state of P D5s and Q NS5s. Now, these 5 branes span directions 0, 4, and they form a non-trivial junction here in the 5, 6 planes. So the supersymmetry condition for this semi-infinite 5 branes is given by PQ charge conservation. This has the additional condition that it fixes the angle which they lie in the 5, 6 plane by their PQ charge. Now, the SCFT lives in the 0, 4 volume. Additionally, we can also take these brainwebs and make them end on D7 brane, these external 5 branes, which span the 0, 4 and 7, 9 directions. So they are points in the 5, 6 plane. Now, these 2 constructions are in principle unrelated. However, if the Calabi-Yau is toric, then the brainweb is dual to the toric diagram. This is a polygon that defines all information about the geometry if it is toric. So for example, here we have a recurrent example, the E1 theory, which is defined by this PQ 5 brainweb with these 4 branes meeting at this junction. So we take the dual, so we take these four faces, which corresponds to these four external dots, and this vertex corresponds to the internal face. So this way we can translate from the brainwave to the toric diagram, and vice versa. So the SCFTs living here have 5D n equals 1 supersymmetry, which have a moduli space which is given by their supermultiplet content. So first we can talk about the extended Coulomb branch, which is given by the vectors of vector supermultiplets. We distinguish between dynamical vectors, which corresponds to the proper Coulomb branch, and additionally, we have vectors which corresponds to background gauge fields of global symmetries, which we will see that they parameterize the mass deformations to these UV SCFTs. Additionally, we have the Higgs branch, which is given by the vectors of hypermultiplets. Now, how does this moduli space get translated in the geometric engineering point of view? Well, this corresponds to desingularizations of the Calabi-Yau, which we distinguish two types. First, we have crepant resolutions, which corresponds to extended Coulomb branch moduli. So we map the singular variety to a non-singular variety, and the singular loci get mapped to so-called exceptional divisors. Additionally, in this procedure, we have non-compact divisors that appear. Then the exceptional divisors correspond to Coulomb moduli, and the non-compact divisors correspond to mass deformations. And the Higgs branch will be given by deformations of this singular geometry. They are given by algebraic variety, so these deformations correspond to just deforming the algebraic equations that define them. So how do we see this extended Coulomb branch in the 5D in the brainwave? Well, they correspond to taking these junctions and opening them up into irreducible supersymmetric triple junctions. The web therefore accepts two types of these deformations. So the first type, which corresponds to Coulomb moduli, are those keeping the asymptotic position of the external fibrations, which translate to just opening up a face. So for example, here in the top example, we have this vertex, which we resolve into these four triple junctions, which are irreducible. We cannot open them up further, and they are supersymmetric. PQ charge is conserved. Now, doing this procedure, we can open up to R faces in the brainwave, which is exactly the rank of the proper Coulomb branch. Now, there is another type of deformations, which are mass deformations, corresponding to altering the positions of the external fibrations. So, for example, in the E1 case that we see here, we can turn on a mass deformation that makes this UV SCFT flow into a pure SU2 gauge theory without fundamental matter or theta angle, which results in this web. And we identify this length here as the Young-Mills coupling. Now, if we have a junction with L external branes, we have L-3 mass deformations. This is because we have the freedom to remove two mass deformations by translation in the 5-6 plane, and we can also have an additional freedom to choose an SL2 set transformation for the whole brainwave. Now, how are this opening up of the web translated to a toric diagram? This is equivalent to triangulating the toric diagram with area 1/2 triangles, each being dual to a triple injection. So for example, in the E1 case, this is fully resolved. So we have the mass deformation and the Coulomb branch parameter turned on. We have these four irreducible junctions that translate to these four triangles over here that we use to fully tile the toric diagram. Now, in general, a toric diagram can accept several triangulations, which are related by a so-called flop transitions. Each triangulation then corresponds to a different resolution of the singular geometry, and the basic flop transition is what we depict here, which comes from the conifold. So it has two resolutions given by these two different brainwaves, which have a segment of finite length. We go from one to the other by shrinking the segment to be length 0. So we recover the UV SCFT that defines the conifold, and then we open up the new direction. So going from one to the other is a flop. Connected components, and each component gives a dimension for the Higgs branch, which is quaternionate. Now, we aren't gonna talk much about the Higgs bands here in this talk, but just for completeness, they were recently studied in the literature by magnetic quivers in toric cases, and these results were extended to GTPs also quite recently. Now, so far we've only talked about the toric geometry, but we can go to define so-called GTP theories by from the brainweb by forcing several fibranes to end in the same 7-brane. This results in some segments that we slide off through the to the Higgs branch. So this is equivalent to turning off the webs of hypermultiplets. Now, these manipulations result in some change in the geometry, which was recently studied in the mathematical literature. Now, this is seen through in the toric diagram in the sense that we don't have a toric diagram anymore, but we have a so-called generalized toric polygon, which includes white dots, as we see here. So, for example, we start here with this toric diagram in the left, and we focus on the left-hand side, which results in this of the junction, which has these three branes, which do not end on each other. So first, we force the brane in the middle, the 7-brane in the middle, to end in the 5-brane in the top. This results in the formation of this segment that we can slide off in the Higgs band. So we end up with this 7-brane with 2 5-branes ending on it. This is represented on the generalized toric polygon as the appearance of this white dot, which means that these 2 fibranes end on the same 7-brane. Now we can do the same thing again and force the bottom 7-brane to end on the stack of fibranes, and this results in 2 more segments that we can slide off, and this results in these 2 white dots. Now, a natural question would be if these GTPs are supersymmetric. And there is a non-trivial condition for supersymmetricity, which is the S rule, which is a 5D generalization of the original S rule proposed by Hanany and Witten. Now, the easiest way to see this S rule is if a GTP fulfills this S rule, is if it is tileable by so-called supersymmetric pieces, which generalize these area 1/2 polygons, which corresponds to two webs which jump over junctions. So for example, here we have a piece, this is a trapezium piece, and it corresponds to a triangle junction over here and a segment that jumps over it. This is what is represented by this semicircle. So in order to check if a general GTP is supersymmetric, we have to use the so-called propagation of the S rule. This is a procedure that starts by first reading the boundary data of the GTP, so the number of white dots. And if we have some white dots, we have to cover them using these supersymmetric pieces. So for example, we start with the GTP on the left and we cover it with some white dots. And this results in this internal white dot that we have to cover again with another trapezium over here. And we end up covering all white dots with supersymmetric pieces. Now, if we aren't able to do this, and the algorithm is unable to be completed, then we say that the S rule is broken and the GTP is not supersymmetric. Now, we can additionally, we can take the GTP and directly compute the rank just from the PQ charges of their external 7-branes using the so-called self-intersection formula, which originally comes from considering the junction as being uplifted in M theory as a holomorphic curve of self-intersection I. Now, then the rank of the Coulomb branch of the GTP is just given by the genus of the curve that is computed this way. A way to see this is to consider the toric case. This is when P and Q are coprime. So this self-intersection formula reduces to twice the area of the toric diagram minus its perimeter. Now we can use Pick's theorem and find out that the genus is given exactly by the number of interior points of the toric diagram, which, as we've seen, is equivalent to the number of faces of the fully resolved web or the number of Coulomb moduli. Now, the non-negativity of the genus of the M theory curve is translated to the following bound for the self-intersection. It must be greater than -2 in order for the GTP to be supersymmetric, which sometimes in the literature is called the R rule, this condition. Now, we can distinguish between 3 cases. So for example, if I is less than -2, then the GTP is not supersymmetric and will break the Ashe rule. If I is exactly -2, then the GTP has rank 0 and is minimally supersymmetric. So this is, for example, the case with area 1/2 triangles. And if I is greater than -2, then the theory has non-trivial rank and its web can be further opened up into a configuration with R greater than 0 faces. Now, a word of caution must be said that self-intersection is only well defined if the underlying web is connected. So, for example, we can have a GTP, which in appearance seems to break the Ashe rule by computing the self-intersection, but in fact is a superposition of two disconnected webs. Each of them fulfills the Ashe rule, as for example in the case of the trapezium we've shown earlier. Now, there is another web deformation that we haven't talked about, which corresponds to taking an external 7-brane and crossing it through in the direction parallel to its monodromic cut. This is called a Hanany-Witten move and does not alter the theory. This is not an observable in the field theory. Now, crossing a 7-brane through the junction sometimes results in the number of 5 branes attached to it to change due to the Hanany-Witten effect. Additionally, as we can see here in the example here of this red 7-brane, that gets crossed, when the monodromic cut sweeps across half of the web, when it crosses another 7-brane, it SL2Z acts on it and changes its direction because it changes its PQ charge. Now, if the GTP has self-intersection -2, then we see that we can perform a series of Hanany-Witten moves to fully decouple all 7 branes. So using the Hanany-Witten effect, we annihilate all attached 5 branes. This is called a trivial junction. Now, what do Hanany-Witten moves correspond in the geometry? Well, for example, in the toric diagram, the operation analog to Hanany-Witten moves is called mutation and was originally studied by mathematicians. Now, an example of this so-called smoothing is the smoothing from the F2 toric diagram to the F0 toric diagram given by this deformation that relates these two toric diagrams, which is exactly the analog to this Hanany-Witten move that we've just presented. So, from the point of view of geometry, then the geometry is defined by the mutated and unmutated toric diagrams or polytopes are related by a flat fibration over P1, where the fiber at 0 corresponds to the original, to the unmutated toric diagram, and the fiber at infinity corresponds to the mutated GTP, as seen by a theorem by Hilton. Now, this can be understood as a geometry, as a deformation of the geometry underlying the GTP that then interpolates between the mutated and unmutated geometry. Now, a similar deformation was seen in the Type IIA analog to these 5-brane webs in the T-brane construction, also quite recently in the literature. Now, also a word of caution, or something important, more or less, is that mutations also leave some geometric data invariant, mainly the Hilbert series, which is something we will make use in the latter part of the talk. So with this, I would like to finish the introduction and then start talking about the primitive T-cones and the role they play in the extended Coulomb branch. So if there are any questions, maybe it's a good time to ask.
I have one small question.
Yeah.
The last thing you said about the Hilbert series being constant, can you just re-explain what you mean? Hilbert series or what?
I mean, in the sense that you can compute the Hilbert series from the original, from each geometry on each side, and if they are related by mutation, then they match, in the sense that they are exactly the same.
So you mean the Hilbert series of the Higgs branch?
Of the Calabi-Yau 3.
Or of the
Calabi-Yau 3, yes, the Calabi-Yau 3.
So using the GLSM.
Okay. That's the Hilbert series you referred to.
Indeed. It is the Hilbert series.
And then along the smoothing, there is no Hilbert series. You're comparing the two. You're comparing t equals 0 and t equals infinity.
Indeed, that is what we are doing. So we don't know exactly, or we aren't confident in saying what happens in the throughout at the generic point of the fiber.
Sure. Well, there is no, yeah. That's fine. Thank you.
So these mutations,
yep.
If I remember correctly, the mutations of the toric polygon, they produce always another toric polygon, Well, Hanany-Witten moves will not produce actually a toric thing most of the time, but they will create white dots. So are you saying that if you do the mutation that is not Hanany-Witten, then still the Hilbert series of the two Calabi-Yau trees is the same? This would surprise me.
Sorry, what do you mean by the mutation?
So if we would make instead of F2, F0, okay, this is fine. But if you take a deeper toric polygon and now you move a segment from here to the other side, then what you create white dots in the, right in the brain web. Now, if you do the mutation instead, as far as I remember, this mutation of the polygon, this will produce the same diagram, but instead with black dots.
Indeed, that is.
Now, now this is the thing that you can actually compute the Hilbert series for. And so, are you saying that this Hilbert series matches the one before? Because this would surprise me. Because it should be, these are two different field theories.
I mean, the Hilbert series indeed matches with this, but there are some caveats. I am going to talk about it later in the talk. So it is you have to make some concrete choice in order for the Hilbert series to match. But I will explain this later.
Okay. Then when we get to it.
Yeah, no worries. Thanks for the question. So let's continue if there aren't any other questions. So let's now properly get acquainted with these T-cones. So the easiest way to construct them is by taking a PQ 5-brane segments with P and Q coprime. So we have a 5-brane which is span between these two 7-branes, and consider an additional decoupled 0-1 7-brane, as we see here in the middle picture. And then we take the 7-brane and we Hanany-Witten cross it, which results in this configuration over here. So the monodromy sweeps one of the 7-branes and changes the charge. And also, due to the Hanany-Witten effect, we have a P 5-branes that are created. So because we have P multiplicity of 5-branes here on this web, then we are talking about a GTP configuration, whose polytope is given here on the left. This polytope is characterized as a triangle whose base is equal to its height. This is equivalent to P. And the other two sides are always primitive. All the interior points on the base are painted white in order to signal that this multiplicity. We also customarily paint all the interior dots of the polytope white in order to represent that they have no moduli. We will explain this further in a moment. Now, if we choose P and Q to be 1, 0, then we recover the area of a half triangle using toric resolution. So, in fact, these triangles are just a concrete case of primitive T-cone. So the corresponding geometric engineering object to these irreducible triple junctions were originally introduced in the mathematical literature. The easiest way to see them is coming from considering toric geometries, which can be split into some parts. Some of them are parts that are called T-cones, which admit a smoothing of some kind. Now, the physical interpretation of the fact that these T-cones are parts of the toric diagram that can be, or the polytope more in general, because we are also talking about GTPs. The fact that they accept this deformation comes from the fact that the T-cone has no extended Coulomb moduli. This is because we can take the self-intersection formula and compute it, and we find that for every primitive T-cone, its self-intersection is -2, so it has no Coulomb branch. Additionally, since it is a triangular piece and the number of mass deformation is given by L-3, it hasn't got any mass deformation either, so it has no ECB moduli. Now, another way to see this is through the fact that they are trivial junction and they can be undone by a Hanany-Witten moves as area of a half triangle, so we have no singularity there. Now, if we take all white dots and paint them black, so we recover the singular Calabi-Yau geometry, then this geometry, these T-cone pieces are just a ZP squared orbifold of C3 because it is a triangular piece with the following weights. And additionally, for a given P, we only have phi P over 2 choices of Q given by this Euler-Stoltian function. Now, we can also consider the case in which P and Q are not coprime. So they have a common factor K greater than 1. So in this case, we are talking about a non-primitive T-cone. Its self-intersection, we can compute it naively, and we find that it's strictly less than -2. This would seem that they are not supersymmetric, but we can reinterpret them as a superposition of K primitive T-cones. Each of them fulfills the S rule. So they are proper bona fide supersymmetric pieces. Now, what is the theory that lives here on the T-cone? We've argued before that they have neither Coulomb branch nor mass deformations. So in this sense, they cannot be opened up further supersymmetrically. So in some sense, they are the irreducible blocks of the ECB if they are built through brane webs. However, we argue they are not trivial SCFTs, since they have at least a ZP one-form symmetry. So for example, we can take the 2-1 T-cone, which can be seen as a GTP built from the toric diagram of E1, which we see this through this is equivalent to E1 through an SL2 transformation and a Hanany-Witten move. Now, this E1 theory accepts a deformation, a mass deformation, to an SU2 pure gauge theory without theta angle, which has a Z2 one-form symmetry. Now, since from going through doing these manipulations corresponds to turning on local BEVs for local operators. These are the mass deformation and also the Higgs branch deformation we do here. So since one-form symmetries cannot be broken by BEVs of local operators, then we claim that the Z2 one-form symmetry is inherited by the 2-1 T-cone. More generally, there is a way to compute the one-form symmetry straight from the toric diagram. And we computed this for all T-cones, for all primitive T-cones, and we check that it is ZP. And there is a conjecture in the literature that claims that the one-form symmetry of a GTP is exactly the same as its toric diagram. So here we claim that all T-cones have ZP one-form symmetry. However, we cannot say much more about the explicit theory living on it. Now, with this said, we can understand polytope mutations using these T-cone tools. Now, a mutation then just takes one T-cone and flips it across the opposite side of the web. So, for example, we start here with this red T-cone, which corresponds, and we want to cross the 7 brane that is attached here through the other side. So we flip the T-cone across the web. This SL2 set acts on these 3 bottom segments, changing their PQ charge, and also due to the Hanany-Witten effect results in this white dot. So the area of the T-cone, as I've just said, changes due to the Hanany-Witten effect in the following way. So if the original T-cone, the base is at distance P from its apex, at lattice height P, more concretely from its apex, if the full diagram has a lattice height H, then the mutated T-cone has a new value of P or of height equivalent to H minus P. So for example, here in this case, we have P equal 1, H equal 3, and we have H minus P, 3 minus 1 equal 2. Now, strictly speaking, when considering the mathematical literature, they only consider mutations where the apex of the T-cone is found at the strict interior of the diagram. However, we'll allow the apex to lie at the boundary, as we see here, in order to study, for example, Hanany-Witten transition of rank 0 GTPs, as we will see in the latter part of the talk. Now, recall that in the toric case, the extended Coulomb branch was built by resolving the singularity, which, in the point of view of the brane web, is equivalent to from the toric diagram, is equivalent to triangulating it with minimal triangles. These were 1-0 T-cones, as we've claimed. Now, the main result of this talk is that, in general, if you have a GTP, then the ECB is built from triangulating the polytope, not with just minimal 1-0 T-cones, but with general primitive T-cones, in a way that fulfills the S rule and doesn't result in any free white dot. So, for example, we have here this GTP, which we resolve by first inserting these 2-1 T-cones on its white dots, and then tiling the rest of the polytope with area 1/2 triangles. And in this way, we see that the ECB is built by taking this polytope and covering it with these tangram pieces of different shapes. Now, this isn't a full story because there are GTPs that cannot be tiled only with these primitive T-cones. So for example, here in this example, we have to introduce this trapezium piece in order to fully tile it. So we need to expand our puzzle pieces beyond these primitive T-cones. Now, The strategy would be to, in order to find these tangram pieces, they should correspond, as in the case of T-cones, to SCFTs without any ECB moduli. So if we consider pieces that are triangular, then we recover T-cones, both in their primitive and non-primitive cases. If we have pieces with more sides, then we have L-3 mass deformations that we have to get rid of them. Now, the way to remove them is to consider that the web is in fact, that the piece, sorry, in fact corresponds to two or to several disconnected pieces, disconnected subwebs. Each of them has no Coulomb branch, and we make several of their external fibrations end on the same 7 plane. These add some constraints between the movement of the mass deformations, and this effectively removes these mass deformations degrees of freedom, locking them. So, for example, we see here that this is exactly what happens in the trapezium we've introduced. We have this triangular junction. In principle, we will have a mass deformation corresponding to this motion over here of this segment, but through this locking, through this GTP boundary condition, we remove it. We call this type of pieces locked superposition. And we also must say that applying the self-intersection formula here fails because the web is disconnected. However, as we see, since they are sums of supersymmetric webs, then this piece fulfills the S rule. Now, in general, locked superpositions are composed of superpositions of primitive T-cones and trivial webs, which are, for example, these segments. We show here some examples. So, for example, we have the trapezium we've already shown, or this 2-2 primitive, non-primitive T-cone, which, as advertised, is just the superposition of two 1-0 T-cones. Additionally, we have some new pieces that were not considered in the original propagation of the S rule paper by Benini, Benvenuti, and Tachikawa. So, for example, this piece in the middle is a 2-1 T-cone locked superimposed with a trivial segment, which results in this piece that, according to the authors of the paper, should not be supersymmetric, but in fact fulfill the S rule. Now, a natural question would be to ask if a GTP can accept several tessellations. In general, this would result in the same theory, but we find some cases in which the field theory seems to change its rank. So, for example, we have this GTP over here, which accepts two different tilings. So, for example, in the top one, which has these two trapezium, we translate to the resolved web, and this is equivalent to the fully resolved web of E1 locked superimposed with a segment. So this segment, what it does is it locks the Young-Mills mass deformation of E1. So we end up with a theory with one Coulomb branch parameter and no mass deformation. However, if we go to the bottom tessellation, we find that we have two T-cones glued together. Each T-cone has no Coulomb branch, sorry. So, but it has a mass deformation given by the length of this segment. This is kind of analog to the toric case of the conifold, except that instead of minimal triangles, we have more general T-cones. So this theory has Coulomb rank 0 and one mass deformation. Both of these tessellations meet at the SCFT point. So we take this Coulomb parameter and we shrink it to 0 over here. And this matches with the web we find from making this mass deformation go to 0. Now, geometrically, these several tessellations that accept different ranks seem to hint that the extended Coulomb branch has a non-trivial structure in general, which is something that we would like to further explore. So with this, I would like to end the part about T-cones and now talk about the algebraic deformations of the BPS Quiver. So if there are more questions, maybe it's a good time to let them. Nice. So maybe we can continue with the last part of the talk. So as we see, we can take a BPS Quiver. We can take a 5D theory, sorry, and associate to it a BPS Quiver, which contains information about the spectrum of its BPS states. But additionally, we can see that it contains data about the geometric engineering Calabi-Yau. If the Calabi-Yau is toric, then computing the BPS Quiver is quite straightforward. We just have to import the technology of Brane tilings. So this BPS quiver, we see it coincides with the 4D n equals 1 fractional brane quiver on the singularity, which is constructed from considering the 3 branes that intersect at the singularity. We can construct then this 4D n equals 1 theory and find that the mesonic moduli space corresponds exactly with the Calabi-Yau we are doing the geometric engineering on. Now, recently, in a paper by Cremonesi and Sa, we have seen that we can take this fractional brane quiver and construct superpotential deformations which are related to zigzag paths in a brane tiling. These are in one-to-one correspondence to external 7 branes in the web. Now, turning on these deformations is equivalent to doing a Hanany-Witten move on the brane web, so crossing their corresponding 7 branes. So, for example, in this paper by Cremonesi and Sa, they explicitly consider the Hanany-Witten analog to the F2 to F0 deformation we've previously shown. Now, our claim is that these superpotential deformations can be seen as the 4D n equals 1 avatar of the Hilton fibration we previously introduced for toric diagrams. When this identification is done by identifying the geometric deformation parameter with the coupling of this so-called zigzag deformation. So this is the map that we claim. So we are going to test this hypothesis by considering these two families of GTPs. So we have, for example, the conifold mod Zn over here. So we have this toric diagram, which is n times the conifold, and this orbifold of C3. Now, these two GTPs are related by Hanany-Witten move. This is the example we've shown earlier, that is rank 0. And we choose them because they are complete intersections, so they make your life much easier when doing computations. And also, when n equals 2, they reduce to toric diagrams. So we can build the BPS quiver explicitly. We have yet to know how to compute the BPS quiver for general GTPs. So before continuing,
can I ask a question about this?
Yeah.
So here you say that the GTP on the right is C3 mod Zn, but that would be without the white dot, right? That would be the toric.
That is true. That is true. It is the toric geometry. So it is kind of like a misnomer. It isn't actually C3 times 7. It is the basic toric geometry we are talking about.
Okay, so then you need to deform that orbifold in order to reach the GTP.
That is true. That was our claim.
Okay.
Yeah, it isn't actually C3 times 7. So some deformation thereof. Yeah.
Okay.
Thanks. Thank you for the question. So yeah, where was I? Yes. So before continuing, let's talk a bit on the algebraic geometry part of these varieties. So, for example, this Zn orbifold of the conifold is taken from this equation that defines the conifold in 4D. So these so we have these 4 coordinates, and we add this orbifold action given by this omega Zn factor. Now, we can, these 4 original variables are not invariant under the orbifold action. So we have to define some new invariants, which are given by this A, B, C, and D. Now, if we give the original UV variables a scaling of 1, then these new invariants have the following scalings. And then we can check that that we can rewrite this orbifold of the conifold as this hypersurface given by this defining equation. So we can change variables and transform this original variety into this coordinate ring, which is a complete intersection as it is a hypersurface, an algebraic hypersurface. Now we can do the same thing with C3. So for example, we have these 3 original coordinates and these 2 orbifold actions, and we define again the invariants that we see here, which if we give X, Y, Z the same scalings, they have these following scalings. And now the defining equation for this variety is given by this. So we can rewrite this orbifold as a complete intersection given by this coordinate ring. Now, we can use plethistic information, knowing the dimensions of the scalings of the generators and the scalings of the zigzags between them, and compute the Hilbert series between each variety. And this seems to show something that isn't very good, in the sense that we find different Hilbert series for each variety. We have made the claim that Hilbert series is a mutation invariant. So if they have different Hilbert series, we cannot claim that these varieties are related by mutations. So they seem to kill our attempts in the water. However, we can squiggle out of this situation by instead choosing some non-trivial scalings for the original variable. So for example, for the conical variables, we choose these scalings given parameterized by these two quantities, R1 and R2. And we also can take this choice for scaling for the C3 orbifold. Now, we can use this scaling information to compute the Hilbert series through plethistic once again. And we find that with this choice, the Hilbert series of each variety matches. So somehow with this non-trivial choice of scalings, then we can make the claim that these geometries are mutation equivalent. So this was the caveat I was mentioning before in order to make the Hilbert series match.
Here I have a question. There are 3 U1s because it's toric. So in principle, you could. So there are 3 U1 symmetries.
Yeah.
So in principle, you can just write T1, T2, T3. You have some, generalized Hilbert series. And now, does it match for all these 3? If you compare the 2, can you do some basis change so that the full expression is the same?
I think that the best way to see them is that they are unrefinement from each T1, T2, T3. So, for example, this is something kind of similar to a maximalization.
No, I understand, but I want to, my question is whether if you really keep T1, T2, and T3, so the fully refined thing, can you find the basis change from one to the other? Or is it just if you basically forget about 2 U1s, you can find 1 U1 embedded here, 1 U1 embedded here, so that you produce 2 series just in T that are the same?
No, I think the way to understand it is taking this, we can take the toric diagram, for example, and compute it using the methods from Martelli, Sparks, and Yau. It's Hilbert series with U13 with these 3 fugacities. What we are doing then is we do this for one side, so for the toric diagram of C3, mod Zn, Zn, and for the conifold mod Zn. And then on each variety, on each different Hilbert series, what we do is a choice of unrefinement. So we choose one U1 on one side.
This I understood. My question is whether you can do it also, for the fully refined one, can you find some basis change that matches them, or can you not?
Some basis change.
Yeah.
I believe so you can try to rewrite them. No.
But if you could do that, wouldn't the toric varieties be the same? Because that's what defines
that's
toric
why
variety.
I'm asking.
I think that the theorems, the mutation theorems that are telling you that the Hilbert series should match, they are not refining this Hilbert series. So they don't. This basis change does not need to exist. I don't think.
Yeah, I think I agree.
Hey, Guillermo, you said that the theorems,
where are these?
They do not involve refining, you say, or unrefining.
Yeah, exactly. I don't remember now. Nacho knows.
Okay, because I think toric varieties are defined just by the cone of generators. So if these cones are the same, so if they are related by an integral change of basis, then they would be the same varieties, but they are not. So so it's probably there is a slicing which is the same.
Yeah, you have to change the slicing. This is the thing. So sorry for the confusion. So we claim that under these changes, the geometries under this U1 choice, the geometries are mutation equivalent. So we will now continue with the explicit example of the of C3 mod Z2 times Z2, which in the n equals 2 case is toric. This is a proper toric variety, and we can compute the VP Quiver through Brane times. So, for example, we get this superpotential, and in order to represent this non-trivial choice of scalings, we choose, instead of giving all the hypers the same grading, we take these 4 apart and give it a non-trivial choice. Now we recovered, we can then compute the Hilbert series from the Masonic space, and we recover the Hilbert series for the case n equals 2, R1 and R2. And then what we do is we turn on a deformation of this type, which is given by the prescription of Cremonesi and Sa, which corresponds to crossing this -1, 7 Brane. And also additionally, we find that under this choice of scaling, the superpotential and the deformation have the same dimension, so to speak. So this deformation changes the F terms that define the Masonic moduli space and give mass to some hypers, which are integrated out. After doing this whole thing, we end up with this new superpotential, which we can check matches with the superpotential from conifold mod Z2 obtained from brain tiling techniques. And we check, we can then again build the Hilbert series from the F terms and check that it matches with the previous case. Now, how do we see this geometric deformation straight from the geometry? Now, let's go back to the C3 mod Z2 quiver, and we solve the F term equations. We can express them in terms of these 4 gauge invariant mesons, A, B, C, and D, that satisfy the defining equation of C3 mod Z2 with these scalings. Now, what we do is we turn on the deformation and the F terms change. So these mesons get some mu corrections. And additionally, we can, the deformation contributes this part. After some redefinition of the variable, we see that this equation gets mapped to this one. So if mu is different than 0, we introduce a new coordinate epsilon, and we do this coordinate change that maps this middle equation to this equation in the bottom, which is exactly the defining equation of conifold mod Z2. Now, this deformation over here was originally studied by mathematicians as being the deformation between C3 mod Z2 times Z2 and to the conifold mod Z2. With this, I would like to go to enter the conclusions. So, for example, we have shown how T-cones are the fundamental piece of the extended Coulomb branch of GTPs. However, we claim that we still don't fully know what theory they realize. They have no extended Coulomb branch moduli, but they are not trivial because we expect them to have a ZP1 Font symmetry. Additionally, we have seen an example in which a GTP can accept several tessellations which yield different ranks. This seems to imply that there is a non-trivial structure on the extended Coulomb branch, which is an interesting future direction to study in order to try to understand this better. We know, for example, that the Higgs branches of 5D theory sometimes accept several cones, but maybe this is related, but so far we don't exactly know how. And additionally, we have supported this claim that Hanany-Witten moves correspond to deformation of the geometry explicitly through this BPS Quiver mutation between C3 mod Z2 times Z2 and conifold mod Z2 through the BPS Quiver. We would like to further study this in the GTP case, but this would imply better knowing the BPS Quiver of GTPs geometries. With this, I would like to finish the talk. So thank you for your attention.
Right. Let's thank Nacho. Do we have questions?
I have a question.
Yes.
Can you say more about what's your, I didn't understand the argument, if there is an argument about why you have a one-form symmetry. I mean, you just compute as if it were a toric diagram, but it's not. I mean, is there an argument, like in principle, it's something about the geometry at infinity, right, of your cone? But here, well, we don't know. So, yeah.
Yeah, I mean, maybe calling it an argument is a bit strong. This is more like an observation. Like we expect this these species to have a ZP one-form symmetry. I mean, this is based on the conjecture
Why?
that
So
the Toric diagram. Yeah, sorry.
You say that the Z2 one-form symmetry of the SU2 theory is not broken on the Higgs branch.
Yeah.
Mm.
I think that's the statement.
Okay.
Sorry?
That's the argument.
So is this clear why this should be the case? Maybe this is obvious that on the Higgs branch it doesn't get broken, but
Well, it isn't broken because going from at least our argument says that we go from this Toric diagram to this GTP by going to the Higgs branch. This would
exactly.
Yeah. So this would correspond to giving a BEV to some hypermultiplet, which is a local operator. So this cannot break the Z2 one-form symmetry. This is the argument, at least for this case.
Just to continue on this, then if you have for instance, if you have SU2 with 7 flavors, which realizes the E8 theory, you can obtain a GTP, which is kind of a big box with white dots.
Yeah.
So then you would paint all the white dots in black, and then you would have a big one-form symmetry.
Yeah.
But so do you claim that the E8 theory has this one-form symmetry? Maybe I misunderstood.
I mean, our argument comes from the conjecture that made in this paper that shown here that the Toric diagram has the same one-form symmetry as the GTP. So in principle, if we compute the general argument would be just that we compute the ZP one-form symmetry, the one-form symmetry in the Toric diagram, and this should match with the GTP. But this is something we don't know for sure. This is just a conjecture. So
this seems weird because you can also make the GTP very, very large. Like you could make the GTP size 1000 for the E8 theory.
That is true.
So this seems to be incompatible with the fact that you have like dualities which relate GTPs of different sizes. So.
That is true. That is a good argument. But yeah, I mean, this thing we aren't like really sure why that it should hold. But this is more like an observation, an expectation. So we don't want to claim this further. I mean, to claim this strongly. It's more like an observation that we expect this.
Well, this statement is already in the papers. I think it's in that paper there.
Yeah,
the
exactly.
claim that the one-form symmetry can be read off from the Toric diagram, paint everything in black, and you can read off the one-form symmetries in that paper, or if not in that paper, in the next one or something like that. So that's not our claim. We are using that result.
Yeah.
But then, so Diego, you understand, right? This point that if you can make the GTP very, very large by like how is this compatible? I'm just confused.
But
Maybe
the one-form symmetry doesn't go up just because you make the toric polygon.
Yeah,
right?
it's not the area.
It's a very strong condition to have a one-form symmetry.
But I thought it was no, but it is because if you make the it's just the GTP. It's just the GCD of the edges. So indeed, it doesn't grow stronger. Okay, then it's fine.
Exactly.
It's the GCD now. Remember, their rule is the GCD of the length of the white dot on the thing, and that doesn't grow. Yes, yeah. So yeah, I made a stupid confusion.
Yeah.
Andrea, you're getting ready to say something?
Yes, I had a quick question for Ignacio.
Yes.
So first of all, thank you for the very nice talk. I just want to ask, you painted a diagram just before the BPS Quiver section, and you had the two versions of the triangulation. It was when you had two different versions of the same diagram.
Yes, this one.
Yes, this one, exactly. Do you have any hint of what might be the deformation of the diagram at the bottom from the algebraic point of view? Like what would be the equation describing that deformed geometry?
I cannot really say much about this. This is just an observation. We haven't really studied this further, so I'm afraid I cannot say anything more.
Okay, okay, thank you, thank you.
Do we have more questions? So just because this is really intriguing me, when we have two, let's say Calabi-Yau threefolds that have the same Hilbert series, or at least you can find some scaling so that the Hilbert series is the same.
Yeah.
So there's some equivalence class of Calabi-Yau threefolds. Is there? Do you know if this says anything about the relation of the 5D SCFTs? So, for example, you showed the conifold mod Zn versus C3 mod Zn mod Zn times Zn. And here, so if we put all black dots, you say it's the same Hilbert series, and now you can actually do the Higgsing to get the white dots, which was then the same as SCFT then on the left. So here it would be Higgsing that stays within its equivalence class. Do you have any interpretation of this?
Sorry, can you? I didn't quite hear.
Did you have any idea what this equivalent class of Calabi-Yau threefolds that have a same slicing or something? What does this mean physically for the SCFTs?
I don't think we can say much about this. To be fair, we haven't like really considered that point of view.
Okay.
Yeah.
Thank you. Do we have more questions? Mario.
Maybe can I ask one? Hello, thank you for understanding that. It was very nice and interesting.
Thank
you. My question is, when I have isolated singularity, threefold singularity, say described by an hypersurface, usually the fact that I can assign some C-star weight to the variables describing the threefold is related to the fact that I have some kind of a conical structure in the Calabi-Yau tree. So that is a C-star cone over a base. So can I see the ambiguity in assigning the C-star weights here that defines the Hilbert series as the fact that when I have a threefold singularity that is not isolated, I can define multiple C-star cone structure in the threefold. Is
multiple, sorry?
Multiple different C-star cone structure in the threefold. Is not clear, and also, yes. And so this also means that it's difficult to define what is the R charge, so the thing that you turn on after that.
Maybe.
Yeah.
Maybe that can be a point of view to consider, but yeah, we haven't.
But indeed, when I have a hypersurface that is non-isolated, sometimes you get ambiguity in defining C-star actions. That's the point.
This,
so it can be related, probably.
That is, yeah, that can be like a way to explain it. We haven't like really thought of it that way.
Okay, and I was wondering. Okay, thank you. And okay, thank you.
Yeah, thank you.
Very good. Do we have more questions? Okay, so then let's thank Nacho one last time.
Yeah.
And we can go off the record.